Okay, quiz 19.2, electrochemical cells. Let's look at question 1. Write the cell notation for a voltaic cell made by reducing iron 2+ ions to iron solid and oxidizing aluminum to aluminum 3+ ions. And so I wrote those in kind of the opposite order. When we're writing cell notation, we should start with the anode, where the oxidation occurs. So we'll put first aluminum solid, and then that is oxidized to form aluminum 3+, and that is aqueous at 1 molar concentration if it's a standard cell. This vertical line represents the phase boundary between the solid aluminum electrode and the aqueous solution of aluminum ions. Then a double line for the salt bridge. Now we're into the cathode, where we have iron 2 aqueous at 1 molar concentration. And finally the iron solid electrode on the cathode. So that is the cell notation for a voltaic cell made in this fashion. Question 2 is to sketch the cell, and we'll go through the labels in a moment. But the cell is going to have, of course, cells can be constructed many different ways. The battery that powers your cell phone certainly is not constructed from 2 beakers of liquid, but in many ways that's kind of the simplest model of a voltaic cell that we use in teaching. So we'll have 2 beakers. They will be connected via a salt bridge. And the salt bridge, what it physically is, can literally be a glass tube that's just packed with like a gel that is infused with ions or something like that. It could also be a damp piece of paper that was soaked in a salt solution. It can be as simple as that. Okay, we'll draw the aluminum electrode. And the copper electrode. They are connected by a wire. And here in solution we have aluminum 3+. Oh, it's not copper. I'm so sorry. It's iron. And we have iron 2+. Okay, so that's a good sketch of our cell. Let's see what sorts of things we were supposed to label. The anode is on the left side, where oxidation occurs. You could also refer to the aluminum electrode itself, the solid aluminum metal piece, as the anode, but I kind of call this whole half cell the anode. And then the cathode. Cathode is the other side, or the solid iron electrode. The salt bridge, so I'll just write it up here, salt bridge. What other things do we need to label? Oh, the direction of electron flow. So the electrons are going to flow through the wire that connects the anode to cathode. Oxidation is occurring here, so the electrons are being lost from here. Reduction is occurring here, the electrons are being gained, and so those electrons must be flowing in that direction, from the anode to the cathode. We could also label this as the negative side and the positive side. The direction of the redox reactions, right? So aluminum ions are being generated. That aluminum electrode is actually being dissolved. If you ran this battery long enough, it would eventually die. And one of the ways it could potentially die is by running out of aluminum here. And then the iron ions are being plated onto the iron electrode. Your iron electrode, conversely, is going to get more and more massive. the direction of ion flow. And so because there is a buildup of cations occurring in the anode from the oxidation of aluminum, we're going to have anions. I'll just represent that with a negative symbol from the salt bridge flowing into the anode. There's a literal migration of ions. They are moving through space and going into the anode there. And then the cathode, conversely, is losing iron cations. It would accumulate a negative charge, except that the salt bridge will provide cations to sort of replace the iron that has been lost. Okay, question 3, give the standard cell potential. So we know that E naught cell is equal to E naught cathode minus E naught anode. It's just a matter of looking those up. So the standard reduction potential for the cathode is negative 0.44 volts. And the standard reduction potential for the anode is a negative 1.66 volts. So negative 0.44 minus a negative 1.66 gives us an E naught cell, or a standard cell potential of 1.22 volts. And our last question: is this a voltaic cell or an electrolytic cell? Because our cell potential is positive valued, then it is a voltaic cell. That means we could put a load here, interrupt the flow of electrons, and force them to do electrical work, force them to turn a motor or heat up a heating coil or something like that. If the potential were negative, then that would mean that we would actually have to connect an external voltage source in order to cause these electrons to flow in that direction, in order to drive them or force them against the spontaneous direction of flow. And so this is a voltaic cell.